Okay, hello, welcome to the class. So a quick recap at the syllabus. We finished most of the machine learning topics on the supervised learning sense, right? We did these techniques, we saw how to evaluate, we finished random forest neural networks. We started going through the hypothesis testing, which is a very classical topic in statistics, used very popularly. So these are not models, these are used in scenarios where you're conducting experiments and trying to figure out if, for example, like in an A/B test where, or like in a medical clinical scenario where people wants to answer the question, is organic food good or not good, or is it really beneficial in preventing cancer, for example? Like what is the evidence? Like how would you reject or accept that hypothesis? If the statistical evidence is not significant enough, what is the point of buying costlier food that is organic, right? For example, things like that. Some things are more relevant, more obvious, things like that have been figured out already, like things like smoking, heavy smoking is very correlated to lung cancer. Right? So there is a very strong statistical dependency there. But you could have done a hypothesis test, then it would not reject the fact that it is not correlated. It would say it is correlated. We accept the hypothesis. So these kind of testing of hypothesis with statistical significance is the topic we were starting to cover. We will finish that off and then jump into the other topics like clustering and stuff. Another thing I wanted to bring up was the fact that machine learning has two very popular paradigms, which is definitely supervised and unsupervised. Supervised, we've discussed. We've been doing all the random forest neural networks. All this we were studying in a supervised sense where you have an input data and then you have an output response or label you're trying to predict or classify. In unsupervised, you only have input data. There is no goal. There is no response variable specifically. So you have to just explore your input data. That is unsupervised learning. So if you see in our syllabus, the clustering topics and the explore these PCA, MDS, 11 and 12 is basically unsupervised learning. So here there is no goal of a variable that you want to predict or anything. You only have a bunch of input feature variables. You want to analyze it given that there is no specific goal. You want to group the data into different groups basically. Similarly, there are some other paradigms. There is semi-supervised learning where, for example, in semi-supervised learning, what you have is, obviously you do have input data, but then the question is, do you have labels or response or you do not have a response variable? The thing is, you do have a response variable available, but the data is mostly incomplete. So you only have, for example, a small chunk of data. So these rows, okay, let's call this the input rows, these input columns, features. Let's call this the Y is the response column, this guy. But the thing is, you only have a small chunk that is populated with responses. For all these rows, you have response available. You know whether, say it's email data, right? Or cartoon example. Say you have like a bunch of so many emails, but only a small chunk of emails, you know whether they are truly spam or no spam, they're labeled. But then we are talking semi-supervised learning. So it's like somewhere in the middle of supervised and unsupervised, right? Semi-supervised. And then there is a bunch of other rows where you do have email data available as well. So all of this is populated, but here responses are not available. So you do not know what the label is. You do not know whether the email is spam or no spam. Now there is two things you could do. One is you can only use this small chunk of data and do supervised learning because here you have X and Y available. You can run random forest neural network, SVM, whatever you will be learning. But the thing is, this is too little data, so your model won't be good enough. Another option is you throw away this data. And now this time you use only this data and you do some clustering. So you do unsupervised learning here. So one option is you do supervised on this. Another option is you do unsupervised on the rest of the data where you do not have labels. Because unsupervised doesn't require label, you only have input data. You try to group the emails into two groups and then you want to see if one group is more spam and another is less spam. But it's not good enough in its own sense as well. So what semi-supervised does is this setting. If you have this setting where partially labeled and rest of it is unlabeled, then you want to use entire data set, then you do semi-supervised learning. So that is another important paradigm. There are techniques for semi-supervised learning. Like one popular technique is called label propagation. So if I do a quick search, label propagation, for example, there you go. So semi-supervised. In scikit-learn, which is popular in Python, you have semi-supervised. Label propagation is available. There are other techniques as well. Anyway, so this will be in the advanced part of the course if we did the second part of the course. In current course syllabus, we are doing supervised and unsupervised, apart from other topics. Now there is another very popular paradigm coming up. It's really being looked up to in most modern setups and like all the fancy companies and stuff. So that's the transfer learning. So I opened this for you. So here the thing is you have one source task or domain. This is referring to if you have one input data here of something you want, some input features and some response you want to predict. Similarly, we have another input data and response you want to predict. Okay, and say you already built a model in your company to finish out this task, to do this task, the source task. So that's your model, right? So that model is giving you some knowledge, right? Obviously, about what it thinks about these variables, like what is spam, what is non-spam, etc. That kind of thing. Similarly, then in the future, you wanted to come up with, you had another task that you had to solve in your company or your research. So but that task is dependent on another data set. One thing you could do is you can just use this data set, build your model, get your job done. Another thing is, if you want to improve that further, if you believe that this task and this task have some relationships or some dependence on each other, then you already have built a model in your company. You don't want to do this independently and build separate model. You want to also take the knowledge you built in your initial model while building the new model for this task. Then this is known as transfer. This idea of transferring one machine learning model's knowledge you learned into another model's modeling is known as transfer learning. This is another paradigm. Okay, I've not read through this blog yet. I've just searched it. I don't know what else is covered in this. But anyway, yeah, it's nothing very specific that I wanted to show. Okay, fine. So coming back to our syllabus, let's open our hypothesis testing slides. And then it is important to know the overall structure of hypothesis test, what is involved. So most hypothesis tests have this structure. You have what is known as a null hypothesis, which is some statement you make about some data or some parameter. You make statement here. And then you have alternate hypothesis, which is the alternate thing. You want to test using data whether null is true or alternate is true. You want to either accept the null or you want to reject the null, which is saying I accept the alternate hypothesis. Okay, so here you write your hypothesis. Things like smoking causes lung cancer. Smoking does not cause lung cancer, right? But this is more, people have studied this, so people know about this. But there may be other things that you really don't know about your data. You want to figure out, right? So things like ads with more color red will get greater clicks by women, and ads with more red in them will not get greater clicks by women. There are two hypotheses. And then maybe you're talking about ads for one specific company. I don't know. It could be clothing, it could be smartphone, it could be lawnmower, whatever it is. And then someone might say some manager, some guy will say that, some business marketing guy, and then you need to support or reject what he's saying, right? You cannot invest money in things that are not true, right? Then that will be a stupid idea. But if for that particular product, maybe red does get 10% more clicks on their ads, then well and good, then let's go with it. Right? So every day, so many things people will hypothesize about your data. But in the end, you need to take a scientific decision because that will impact your bottom line, because whether you're taking the right decision or not. So these are different examples. Right? So you write down whatever you think null, alternate in your situation here. And then you want to go with one. This is a setup. And then the way on the technicalities, what the overall structure is what I want to talk about. Once you state your hypothesis, you also have data, obviously. What you want to do is, what they do in hypothesis testing is, so you have your data, let's call this your data. Right. So what they do in hypothesis testing is, from the data they compute in the next step, once you state your null and alternate, is what is known as a test statistic. Test statistic is a, some sort of a formula or some sort of computation that you do from your data set. Now, the test statistic also has a distribution. So since your data is just a sample of the true reality, right? You're collecting a sample of ads and doing, or you're collecting sample of patients to figure out lung cancer versus smoking kind of thing, right? So there is a variation in the test statistic as well when you compute the test statistic. So the test statistic has when there is some variability in everything, it has its own distribution, right? So maybe it is something like this. Different test statistics have different distribution. Like a cartoon example I'm drawing. Maybe it's a distribution of this kind, right? Where, for example, for some null and alternative chosen that test statistic, you know that for lower values of the test statistic, there is a higher probability. This is probability, right? This is what a distribution is, right? Or like counts in histogram. Frequency. This is test statistic values on the x-axis, right? And say higher values of test statistic are less probable. So which means once you go beyond beyond this threshold, observing a test statistic more than this value is very unlikely. Rarely you see. But when you're seeing test statistic value somewhere here, then it is more likely, right? So now the test statistic also has another thing going on, which is the test statistic that you're computing from the data. You assume that you're computing it under a situation where the null hypothesis is already true. So this is like initially you assume something and then you use the data and test statistic to either go with your assumption that null is true or you reject your null. There is a kind of a philosophical reason why you first assume that the null is true already, right? Why not assume alternate is true and then run some analysis and test it? You can say, oh, okay, from my analysis, first I assumed alternate is true, but my analysis says it is not true, so I'm rejecting that. Why are you by default going with null, right? You could have done either way. Math could have worked either way. The reason is usually in null, people put things that are like, if you had no knowledge yet, you not generated this knowledge yet on what is true, then it may be safer to assume that null is true. So a nice situation is like in justice, right? Like in crime and justice and all that, in judges and stuff, and in the law, people assume that. So without knowing also anything, like see, I've not taken any evidence from the crime scene, or I have no evidence yet, but still people will assume that the accused person is innocent. So by default, without doing any investigation, like I'm just sleeping and I'm assuming that this guy is innocent, if I were the judge. That is what is done in our society. That is what we are assuming even before any intelligence. And then people do a lot of analysis and this and that, lot of studies and everything, right? Lot of investigation and hunting around. And then based on their final analysis, then they decide whether their initial assumption they will stick to it or they will reject it. So you're innocent until proven guilty. So here it is innocent, alternate is guilty, but initially you assume that. So because ideally you are okay with making one kind of error versus another kind of error. Like you're okay with leaving a criminal as being innocent, which is an error, right? Versus you never want to commit an error where you say an innocent guy is a criminal and you hang him or put him in jail. That is the reason people do this assumption. Anyway, so now you do analysis, and then what is the idea of the hypothesis testing? Statistical hypothesis testing as follows. You assume that the test statistic follows this distribution. I said test statistic has a distribution, right? Something like this. For some other problem under null and alter, I have another test, it has another behavior of this distribution. But anyway, but I will know that the test statistic, like some theorem will be there, that I will always know that this test statistic will have this pattern of distribution for this kind of a hypothesis test. This particular, if I'm populating this with some specific question, then I know it will be that kind of a distribution. But also under the case that if null is true, because if the alternate was really true, then this distribution will be very different. So I have knowledge beforehand when I build a test statistic that from the data, the test statistic I'm building will have this distribution, will guarantee have this distribution only under the case if null is true. If null is, so this is the thing, if null is true, then the test statistic that I'm building will have this distribution. If null is not true, it will not have this distribution, it will have some other behavior, right? maybe something else. Maybe these values are less probable, and then as you have larger as amount, or something else. Maybe you have some other pattern like this. A lot of everything else other than this could also be possible, right? So you have so many other possibilities when if alternate was true, for example. But we are not caring about that. All I'm saying, if null is true, test statistic will have. Now what I will do is, I state my hypothesis, I build a test statistic, and then I will really look at the value that I observed in the test statistic. If I, in one particular situation, if I got a test statistic value that is somewhere here or somewhere larger than this amount, so if I get some value this big, then I would say, hey, if the null were true, the distribution should have been like this, and these values should have been more likely, but I observed some value of the test statistic that is highly unlikely. Like it is extremely unlikely. Like in 99.99% cases, this value of test statistic should not be happening. It should be much lower than that. So then since I observed something that is very much unlikely under the case that the null is true, then I will say I reject the null hypothesis, which means I go with the alternate and I rejected this in this situation. So then I will say, okay, yes, this is the thing. Now, if I observe a test statistic, something that is like this, or somewhere in this band, right? These kind of values, which are very highly likely, high probability values. Then I will say, oh, what I observed is very much as expected. So I will reject alternate. I will go with the null this time, and I will reject the alternate this time. So that is how, this is the overall structure. All that changes from one hypothesis to another is, what is your null, what is your alternate? Is it lung cancer, or is it something else you're testing? Or are you testing whether average lifespan of men is same as average lifespan of women, or average lifespan of men is lesser or greater or not equal to, right, than women? That's another. So here you're testing a hypothesis just based on averages. Another ads, one thing was like you're testing dependency, right, in ads or in lung cancer kind of thing, between one variable and another, one action on another action, one variable and another. Similarly, you can test hypothesis on variances. You can say, hey, there is more variability in the weather in New York versus in Alaska or something like that. Now, is it true or not? Again, same thing. You take data, you generate test statistic, you assume test statistic is going to is true. You assume null is true initially, and then you know by theorem that test statistic has specific distribution. Then you literally see if your computed value is falling within that distribution, high probability behavior, low probability behavior. If it is low probability behavior, you reject null and go with alternate. If it is high probability behavior, you accept null and reject the alternate. Okay, so this is the overall structure. Now, your choice of how much confidence you want to have on your hypothesis. If you want to be 99.9% confident on what decision you're taking, then this threshold that you're taking in terms of what is probable and less probable will keep on increasing. If you take a very high threshold, so this is say 80% accuracy, 90%, here 99%. If you see a value greater than 99%, then you have 99% confidence. So this is known as the rejection region. This is the acceptance region. So if you fall in the acceptance region, you're accepting null. If you fall in the rejection region for your test statistical value, you're going with the alternate. So that is the overall structure. Now, if I just show you some slides, now you will connect with this. Okay. All right. Okay. So this is an official slide. If you see the elements of hypothesis test, you have a null hypothesis, some statement you're making, alternate, which is contradicting the null, so another statement you're making. You want to go with either. Then there is a concept of test statistic, right? Quantity based on sample data and null hypothesis. See, test statistic is always linked to null hypothesis. Used to test between null and alternate hypothesis. Right? So if the null was true and based on your data, if you compute this quantity, you have it some distribution. And see, if now you have a rejection region. Okay. Let me know if I'm at some point the screen share stops or hangs, but for now I'm assuming it is fine. So now based on the test statistic, you also have, assuming null is true initially, then you also have a distribution. So in the distribution, like I showed, based on your threshold you're going with, you have a rejection region, you have the acceptance region. So values of test statistic for which you reject null is known as rejection region. In which you accept null is known as acceptance. Right? Now, different kinds of errors you can make, right? This is the true state, this is your test result, right? So if the truth is that null was true, and if you took the correct decision through your test statistic, all that analysis, then you made a good decision. Similarly, if the truth was null was not was false and alternate was true, and if you made the same decision, then correct decision. But you can make two kinds of errors where you can say null, when null is true, your test might have, your analysis might say null was false. Then you made what is known as type 1 error. If null was false and you made a null is true, then it's a type 2 error. So type 1 error is, the probability of a type 1 error is denoted by alpha, probability of type 2 error by beta. Always alpha beta has become like a common notation for type 1 and probability of type 1 type 2 errors. So ideally you want to reduce these errors, you want to improve your number of correct decisions. So our goal is to keep alpha and beta reasonably small. So low probability of type 1 error, low probability. Right? Because in this example, if the truth is that lung cancer causes smoking causes lung cancer. That was your null. Smoking does not cause lung cancer was your alternate H1. And then if you made a right decision, okay, but when smoking caused lung cancer, you said does not cause it, then you made one kind of error, etc. Okay, so one example, say in pharma companies, a lot of clinical trials are run for new drugs and stuff that people come up with, like new medicines, antibiotics, whatever, treatments for different illnesses and conditions. So you want to be statistically very sure that what the company is promising about the disease being reduced by the drug is true, that it is efficient, and it's also making sure it's not causing bad side effects, right? So on the efficacy, you want to run a test, right? So say if I just keep running ads and showing people that come buy my new medicine, new drug that I've developed, it will, cure all your illnesses. If I just make statements and if the truth is other way around, then people can arrest me, right? Or people who are really dying who are using that drug, I'm kind of killing them because they're assuming it will work and it's not going to work. And they're paying a lot of money, right? It's like a fraudulent thing. So ideally, you don't want to be in that extreme. You want to be in another extreme where, the drug is, on 99.9% people, it is improving the situation or curing the illness completely, and it is very few percent it is not working. It's causing side effects or not working as required. Then that is high efficacy. But how do you decide this, right? People can come up with all statements like, how do you make sure this is statistically true? Because you're selling it to humans and it is direct impact on human life and, safety and everything. So here you want to run these clinical trials. Then you have to run experiments. You have to take patients, you have to take healthy people, run and see how different it is. So one kind of experimental treatment is the follows, where you look at before and after, or you can also look at a group that has illness that received your drug, a group that has illness that did not receive the drug. And then your parameter of interest could be what is the average improvement you've seen, or average between one group to other. Different kinds of setups you can have, but regardless, you would always have some hypothesis test to go with one drug or the other. So one hypothesis could be new is better than standard treatment. So the effect is not zero. So it means both are not same. Is no better. So effect is zero. Or effect is less than the effect of the standard treatment. So here less means standard is better, right? Similarly, if it is equal to zero, it means both are similar performance. So no point for new drug. Other is new is greater. So if you see new is greater than standard treatment, right? Which means new minus standard is greater than zero, which means alternate hypothesis. You want to go with one, you have sample data. Lots of people, healthy, unhealthy, everything. You're doing a lot of clinical trials. You're literally injecting that drug or giving him those tablets, everything. You collect some data. Now you have to decide statistically. So here it is truly a test of means, for example, averages, for example. So like I said, there is a test statistic, there is a distribution, right? Now you see a lot of math going on here, but this formula you see here is known as the test statistic. It is a popular test statistic for comparing the difference in averages, difference in means. And there is a theorem that this test statistic is normally distributed with this mean and this variance. So you know the distribution as well. I can plot, I know what shape it is. So based on that, I know what is acceptance region, what is rejection region. So test elements, right? Test statistic, rejection region, observation region. So if I say if it is greater, if this based on this plot, I know which is less probable. So if it is greater than that value, then I reject. Otherwise, I accept. So if it is greater than, see, this is the normal distribution, right? One specific normal distribution. If it is greater, then I reject. If it falls here, what the value of test statistic I computed greater than this value, then I reject. If it falls here, I accept, right? So this probability in this rejection region, you can, if you want more and more confidence, you can move this threshold higher and higher. Then only if it falls in this part, then you will say it. This is known as the p-value. The probability in this part of the thing is known as p-value. Okay. Now there are many kinds of tests.
Can you go back?
Here, right? Yeah.
Yeah, what is it? Probable generalization and then the recount.
Okay, yeah. So I will just show the parallel thing we had here. Same thing going on. So the test was, say, for some difference in means, right? Average effect was different or not good enough. Or another one, alternate was saying it is more better. The average effect of one drug is better than standard treatment. You took data, you computed test. The overall structure is same. So you computed one test statistic. In this case, the test statistic is for the difference in means, right? Is this thing. So your Y1, Y2 are your averages that you observed, and this is like the S1 and S2 are like what is the standard deviation or variance of the average you observed here? What is the variance of the average you observed in this drug? That's other drug. N1, N2 is how many people received drug 1, how many people received drug 2, that is N1 and N2. So everything is known basically from your sample data that you collected in this table. From this table you can compute this value and this value, right? And like I said, this value is now this value basically. This test statistic for comparing means is that value. And the test statistic that I showed you in the slides, this thing, is known as, and also the fact that you're comparing means, this test statistic has a popular name. It is called t-test. There are different kinds of t-tests, but the one you're seeing is a t-test. So it is a test statistic for comparing means anyway. Next thing, going to that p-value, right? Now next what I said in the next thing was, once you have a test statistic under the assumption that null is true, you know what its distribution is looking like. So now you need to know what distribution that t-test test statistic has. So what distribution does this have? Now the theorem is, since you know that, for t-test people have proved, like in this statistician called a while ago proved that this is a classical test basically. It's very well known. So they proved that this quantity always will have a normal distribution with this variance, this normal with mean this value and this variance this value. So it has one specific shape. That's what I meant, right? So test statistic, you know when null is true, it has one specific shape where you know what is the probability of every different kind of value that you're observing. So normal distribution usually has this bell shape, this kind of shape. So this is one normal, this is another normal with lot more variance, but it has this increase decrease kind of shape, both symmetric on both sides. Both sides look similar. It's known as the bell curve. So this test statistic for comparing difference means is this, and it has a normal distribution. That is what this showed. Now you know the test statistic and you know what is the distribution. So this is a normal distribution. That is what this cartoon is, what you're asking about. Now the next thing I said in the structure of hypothesis test is the following. Now once you know this, you literally compute the test statistic and then you see if your test statistic you observed according to this distribution is highly likely with high probability or less probability. Because you're assuming the distribution when null is true. So if you see something that is even more unlikely than it should be observed, which is like these kind of values where the probability is very low on the y-axis, right? Then you say, I reject the null hypothesis. If you find smaller values where probability is high, then you say you accept the null hypothesis. So that is what is being shown here. Since I said that test statistic that we computed in this test statistic has normal distribution, the normal distribution looks like this. Now you can put some cutoff and say these probabilities, these values are less probability. These values are also less probability. As you see, these values are high probability. So if you observed something, I can cut off here and say if I observed something in the middle, then I accept the null. If I see something, this tail value, these small values on the x-axis for the test statistic, then I reject the null hypothesis. Then this is known as a one-tailed test, because now here is not, for some reason, although these values are low probability, he's not considering these. He's only basing is based on large values, because he's considering a situation. What is one-tail, two-tail? Let me tell you that. So there are different kinds of tests you can do. One is if you had an equality situation here, if you put an equality, new treatment of new, average effect of new treatment versus average effect of standard drug treatment is the same, then it is, and here if I say not equal to as my alternate, then that is one kind of test. But if I put less than condition here, greater than here, then it is one tail test. I'm only caring about one tail. Other way around, if I put greater than here and less than here, then it is other tail you're caring about. Because you don't care about small values. See, here you care about larger values. This is a one tail test. So now if you observe something for that test statistic, from your data you compute this value, and then if you observe it falls in a value larger than this z observed, then this threshold, then you would reject it, because this is low probability event. If null were true in this, then this is the distribution, then you observed something very unlikely, which means null is not, very likely that null is not true. So you go with alternate hypothesis. That is what this is. Any clarification you got? Some more you want information?
No, I got it.
Yeah. So that is it. So as you see, everything put in one page here. You made some null statement, null hypothesis. You made alternate statement on the average behavior of one thing versus another. You said they are equal to 0 means there are no difference in the average behavior. If it's greater than means population mean 1 is better than population mean 2. Right? This could be a drug thing, some cancer thing, something else, some advertising thing, but this is a test on means basically and averages. So then you have a test statistic. Then you have the distribution, which is the normal distribution. There is a theorem. This will always have normal distribution. That is the beauty of it. So now you know the distribution. Then you, based on a cutoff value, you know what is rejection region, what is acceptance region. If you observe something very unlikely, then you reject the null, because this is this thing will follow that distribution only when null is true. That is the condition there. So this shape will only be there only if null is true. So if null is true, then you should be observing more likely things more often. If you observe something very unlikely, then null is more likely not true. That is what the idea is here. So based on that cutoff value, you will see if your observed value of the test, this is the test statistic z observed, he's calling that. If observed z is greater than the cutoff threshold, then you are rejecting. If it is less than that threshold, you are accepting. Reject H0 if test statistic falls in rejection region. That is the idea. Different examples. Botox, I don't know, I'm not a doctor, but Botox looks like some injection, right, for cervical dystonia. Different conditions for women or something like that. So patients, individual response, then placebo, they have two groups. Placebo means they're receiving a drug, but basically that is just a sugar pill. It doesn't have any medicine in it. That is a group of people you're testing this drug on for this condition. Then the drug in another group you're giving you're giving this drug. But you're not telling the people. So that because sometimes, when you're suffering from something, I give you just a sugar pill and I act like this wonderful pill, this will reduce everything. The fellow might have like some, psychological effect, and he might think, oh, it is really improving sometimes. Unless it is not a major condition where he clearly knows he's in pain or something. So you don't want that kind of a bias. So you don't tell them which group is receiving, which is not receiving, but you know as an experimenter. So one will only receive sugar pill, means no treatment. Another will receive real pill. Then you will see average response, how the severity is, right? You do this for, say in group 1 you had 33 people, group 2 you had 35 people. See, because you cannot always collect same number of people. Sometimes you might have difference, right? Because if you are testing a drug for some very rare kind of a cancer, rare condition or something, you cannot get like 1,000 cancer patients who are really suffering in their life, with a rare cancer. It's a rare cancer. You cannot also, socially you cannot get a agreement from 1,000 people. They have their own issue that they're fighting in their life, right? So sometimes this might be very imbalanced also. So you need to take that condition into note. And also obviously the response you're observing will have different variability. Here looks kind of similar, right? Then here you saw average response is these values are average response. You saw 10, 7.5. Based on that, then you don't know if this is given this variability and this difference and these samples, you don't know if it is statistically one is better or not better. So now you are running this test. This is same, one is better than the two. And this is the test statistic. Here he literally plugged in those averages and these things into the formula that we've been seeing all through these slides. He got this value. Now he knows what the cutoff is supposed to be. If it is greater than that cutoff, you reject, otherwise you don't. And apparently in this case, Botox A produces a lower mean score. So yeah, so he went the other way. So he rejected them. He rejected this. Anyway, two-sided test means if you see here, in the alternate I had only greater than one side only I'm testing the tail. Here two-sided test means two-tailed test. Here you are seeing not equal to means it could be greater, it could as well be lesser. You don't know. As long as it is not equal to, you want to go with alternate. If it is equal to, you want to go with none. So here you will look at two tails. Both sides you want to, you will have to see the tail. Okay. Now an extension or a parallel topic of hypothesis test is known as confidence intervals. This thing we will cover, I guess, in next class because we are 1 hour done. But I would not dig too much into confidence intervals. It's actually a very parallel concept to hypothesis testing. In confidence interval, if I am asking to compute something, you will give some band also. So you will say, if someone says, so this is an interesting thing. Some drug someone came up with, zone for HIV-1 lipotrophy, right? Now we want to test versus placebo whether there's a difference in HIV treatment or not. So in confidence interval, whatever statement I'm making, I will give some error bar around it. So if someone asks me a question, what is the probability that India will consecutively win its next 3 cricket matches? Or United States will consecutively win swimming gold medal in the next 5 Olympics consecutively. Right? So which 5 Olympics means like in the next 20 years, every 4 years, right? These kind of questions, right? Then I will say, I can act like a wise man and say, hey, the probability is 70%. Or I can be even wiser and say probability is 70 plus or minus 5%, which means I'm giving a band now. It is between 65 and 75%. Now my probability and my band could completely be off, means I'm bluffing or my calculation is wrong, either way, right? Or it could be perfect, right? So, but the idea is once you give a confidence interval, when you do proper statistics analysis from your data, when you make a statement and when you give an error bar and you say with 95% confidence, what I said will fall within this error bar, within this plus or minus value, then that is known as an interval. Interval in what is interval in math, right? It's just a interval, right? From 3 to 5 is an interval, anything between 3 and 5, closed interval, open interval, right? Similarly, confidence intervals. If I say whatever I'm saying, if I give an interval and say I have 95% confidence that it will fall in that interval, then the probability in my confidence is 95%. If you want a 99% interval, then maybe I have to increase the size of my interval, right? Because I'm not very confident then. If you want 100% confidence, then I will say the probability is between 0 and 1 that US will win next 5 gold medals in next 20 years in swimming. Because probability has to be between 0 and 1, then I have 100% confidence, but my interval is useless, right? Everyone knows it is somewhere between 0 and 1. But if I give you a more useful interval, ideally I want a small interval. I should be able to say, hey, probability is between 20 and 30%, or probability is between 25 and 35, or between 90 and 95, or 95 and 100. So that is the idea of confidence interval. It can be computed directly from the idea of hypothesis test only, the test statistic, confidence distribution, all that. So the idea is overall this thing. We will discuss little more next talk, where I showed you this plot, right? So I can say, if it falls between this value and this value, then there is high confidence because you see high probability. If it falls between this value and this value, low confidence, right? So based on what I am stating, if the true observation ended up here, then I know if I want high confidence, I know what is the size of my interval I need to take because I can sum up this probability area under the curve. That is the overall idea. So it's just an extension of hypothesis test idea. It's the confidence interval. They're kind of parallel concepts, very related to each other. So coming back to the slides, one thing I wanted to say was on where we are and when we will finish. That is also important. So we finished week 9. Confidence intervals I will not cover in great detail, but I will cover. So we had more detail in hypothesis, but here I'll slightly lesser detail I will cover. And by the way, clustering and this topic, these things can be grouped together. So what we will do is we'll cover a little bit of confidence interval and a little bit of clustering next slide. next class, and in the following class again leftover clustering, and the week 12 will cover in the following class. And if required, if you want an extra revision, we didn't do this in specific, we can do this. I think we spend the revision topic to discuss about job interviews, or I think some assignment and that kind of thing, right? So we can always do another like that based on your request. I'll be open. Okay, so that is the call for today. Let's call it a day. Feel free to email me any questions, but also try to focus on the assignment or project. That is very important for your job. Not even data science. If you're applying any role, right? Even software developer role, accounting role, manager role, you need to have some projects you need to show on your resume. You cannot just say I took a course in here, unless you took a course in MIT or something, like not online, like really in there. Then people may believe you, but otherwise just saying I took a course somewhere is not good enough. You need to do some projects. Okay, so have a good one. Good weekend. See ya. Any questions?
Thank you. Very good.
Okay.
Thanks, Pranit.
Yep, welcome. Bye.